Welcome to the LAD series, Episode 1, The Quantum Threat to Digital Signatures. Today we will set the stage, why every certificate on the internet is on borrowed time, and why hash-based signatures are the conservative answer.
Today's web runs on RSA and elliptic curve cryptography. Every HTTPS connection, every signed software update, every banking session, every authenticated email, all rely on one of these two families. Both are based on hard math problems. RSA relies on factoring large semiprimes. Elliptic curve cryptography relies on the discrete logarithm problem on a curve, on a classical computer. Both of these are believed hard.
Then in 1994, Peter Shor changed everything. He published a quantum algorithm that factors integers in polynomial time. The same algorithm also breaks the discrete log problem. What this means in plain language, on a sufficiently large quantum computer, RSA and elliptic curve cryptography collapse from hard to easy, not slower, not weaker, broken.
And here is the catch. Adversaries do not need a quantum computer today. They are recording encrypted traffic right now, to decrypt it later when the hardware arrives. This is called harvest now, decrypt later. Signatures have an even more pointed problem. A certificate issued today may still be valid when a quantum computer becomes available. A forged signature on a long-lived document would be indistinguishable from the real one. The clock is already ticking.
Throughout this series we will follow two characters, Alice and Bob. Alice signs documents. Bob verifies them. If a malicious party can forge Alice's signature, Bob has no way to tell the real document from the fake one. That is the entire stake of this series.
Cryptographers have explored three main directions for post-quantum signatures: lattice-based, including MLDSA, which NIST standardized as FIPS 204, hash-based, including SLHDSA and SPHINCS+, which NIST standardized as FIPS 205, and code-based, like classic Michaelis. All three are believed to resist Shor's algorithm. They make different bets on which math stays hard.
Hash-based signatures rest on the smallest possible assumption in modern cryptography, specifically, that the underlying hash function, typically SHA-256, is hard to invert even with a quantum computer. Grover's algorithm gives only a square root speedup, leaving roughly 2 to the 128 quantum work. To break SHA-256, there is no new mathematical structure for an attacker to exploit. There is no exotic assumption that might be broken in 10 years. It is the same primitive that already secures almost every other thing on the internet. That is why hash-based is the conservative choice.
And this is where LAD fits in. LAD is a hash-based one-time signature scheme. It belongs to the same family as Lampert, SPHINCS+, and SLHDSA. It rests on the same security foundation, SHA-256 preimage resistance. LAD's contribution is engineering, not new hardness. We use a compact witness built from additive prime decompositions, yielding signatures around 100 bytes, compared to 17 kilobytes for SPHINCS+. LAD does not invent new cryptographic hardness. It packages an existing assumption more compactly.
Here is what is coming in this series. Episode 2, The Pure Math, Additive Prime Decompositions. Episode 3, From Math to Signatures. Episode 4, Certificates and X.509. Episode 5, Standards, the IANA Object Identifier, and the OpenSSL Walkthrough. Episode 6, For Cryptographers, the paper, the code, and the cryptanalysis challenges. Each episode stands alone. Watch the whole series for the full picture.
The paper and the code are on screen. Up next, Episode 2, The Pure Math. One honest caveat before we go. LAD is a candidate scheme. Community cryptanalysis has not yet taken place. We recommend using LAD as a hedge, alongside an NIST standard, not as a sole replacement. Thank you for watching.